where we will go through a topic on leveraging AI and machine learning and digital twin to optimize wells operation, a step forward, a step towards autonomous decision making. A little bit about myself. Tingnan dito, I am Tengku. Huh? Tam. So I am Tengku Azharuddin, Tengku Bidin, from Besut, Terengganu. Started in the industry in 2002. 7 years in mud logging services, and then about 12 years in Halliburton Sperry drilling, focusing on real-time operation. So January 2020, I joined Fast Technology as head of digital operation for drilling. So more or less about 23 years of in the industry. A little bit on Fast Technology. This company was established in January 2015 by our founder Haji Hamid Ahmad. As an example of our solution and services deliverables in drilling domain, we provide to our client a vendor neutral data integration and visualization software, Sitecom, from Cosberg Digital, Pronova performance benchmarking, and then digital twin real-time transition drilling dynamic software by Secal. So let's go into the agenda. So throughout our session, we will go through topic related to digital twin, role of AI and machine learning in wells operation, a little bit on the integration technology, the benefit of integration, and then I will go through an actual case study from a drilling automation project that we done with our client. So this is a 2-hour session. Although we have a Q&A session at the end, if you have any question, just raise your hand or type in the chat. Anissa will inform me on if there is any questions. Okay, now, as an introduction, it's good to look back how all this developed throughout the journey. Digital transformation more or less started. The technology started at about around 1950s, 1960s, where the foundational technology was developed. During that time, it's related to document exchange. It could be say that it's the fundamental of the development of supply chain management. And then we go into e-commerce era. That's in 1979. There's an innovator by the name of Michael Aldrich. He invented the tele-shopping, where he connected TV to a computer. So from there, it's kind of revolutionized the data sharing and kind of a hype in that era. So in terms of oil and gas sector, this is kind of influence data sharing and operational efficiencies domain. So it enhances capability to communicate across global change. uh, come in, and then the in 1990s, we people call it the internet boom. So the generation of internet started there. So it kind of start up the enhancing the communication technology. In the 2000s, the infra for internet and communication start to be upgraded. We have that time 2G, 3Gs, and then until today, and 5Gs, LTE connections. Um, in terms of oil and gas industry, when we try to search in the web, a lot of reference go to World Economic Forums held in 2015, where topic related to digital transformation uh, was recognized as a critical driver for the change in oil and gas industry. Excuse me. So integrating technologies such as IoT, AI, big data analytics, to further enhance operational efficiency. Like Petronas, they also begin to explore digital technology within this period. Um, in 2017, company like Aramco, Petronas as well, start to have their own programs, leveraging testing, doing pilot projects on IoT and big data analytics. And then come the COVID era. We like it or not, this pandemic is actually a catalyst towards a higher adoption rate of digital technology. So lockdowns, works from home, travel restriction, and all the other restrictions have accelerated the digital transformation around the world. So next, when we talk about digital transformation, it's a journey. So each organization needs to have a plan, a proper plan. I think nowadays it's easier, but post-COVID, um, it's a challenge for an organization. I take reference to Oil and Gas IQ. This article was written by Diana Davis. So she highlighted 7 factors for successful digital transformation. One is the connectivity. This is a crucial component. So if you don't have adequate bandwidth, you will have limited data transfer rate. Of course, slower rate, longer time to transmit your document, your image, or whatsoever. Um, for example, when we consider a live CCTV video feed, um, a bandwidth from a remote location like your rig site somewhere in the middle of South China Sea, if you don't have the bandwidth, it's impossible to transmit a clear, smooth live feed. Like BP, they roll out 1,280 kilometers of fiber optic network in the Gulf of Mexico to enhance their operation at offshore sites. So fiber optic in Qatar as well, they use also fiber optic. So data transmission, everything is very, very fast. So connectivity is the first factor. Readiness of the organization and technical system. So focusing on both its culture and technical system, it's essential to ensure that the organization support the change and is willing to allocate resources. Well, digital transformation, digital uh, work or processes is not cheap. It costs you a lot of money, and then that's the reason why you have to plan properly, do testing, do maybe trials, proof of concept exercise, and then when you want to integrate a legacy system, it can obstruct progress. So both the organization as well as the service provider actually have to move along parallel too. So when the organization updates something, the third party, the vendor also have to also go to the journey of enhancing new technology into their system. um, Next is focus. So it's obviously critical to maintain focus for a successful digital transformation. Then improve process. So obviously, when we go to this journey, we definitely want an improved work process. Either it's related to cost, related to time, related to safety. So all this, you can't really speed up things if the process is inefficient. So tweaking here and there, it's not gonna do many benefits. So you have to sit down, create a focus group to find your actual pain point to come out with a better process workflow. Once that's in place, you have the system. You will need to get it to your user, to your for them to test it, um, and then giving back feedbacks. So we are changing their workflow, their work process, and definitely we will need their feedback to further uh, enhance or improve the system that we want to implement. So skills, um, this is a gradual process, much like painting. Some people say. So if you if you given a professional to paint your portrait or whatsoever, it will he will want a longer time to finish it. So it can give you a lot of better improvement, better details on your picture. So organization should begin with small steps, steadily their activity, and recognizing potential improvement will uncover new opportunities as they advance. And oh, okay. Um, and then lastly, the journey. It's as mentioned earlier, it's a long-term journey, not a one-time event. It involves with technology advancement. So do not be discouraged because it's a work process. If it's not finished yet, you have to be patient. But of course, we need to see progress. So focus on the continuous improvement and adapting how employee engage with their task. So that's on the digital journey. We'll look into a little bit on the importance of digitalization. So we should expect operational efficiency to increase. So by using digital tools, it should streamline our workflow. So by that, it will reduce manual errors. It will also enhance your data accuracy. Moreover, automating this process with digital tools should free up valuable time for engineers and other professionals to concentrate on what truly matters, such as focus on strategic decision making. Um, so this digital tool will definitely eliminate the repetitive tasks that you have to do while analyzing data. So identifying trends, we should expect that, uh, and it should also extract proper insights for you to make better decision for the business. Next will be safety enhancement. So once we have the technology, then we develop uh, sorry, it's real time, of course. Um, by incorporating technology, we can reduce risk. So real-time monitoring in a remote operation, you can downsize the manpower at your operation site, move that, so you have less manpower over there, but still work in the time of the work and what was performed on the rig site was is not affected. And then once you have the technology, um, you can develop a predictive analytic. Why? Um, Technology can help us analyze data trends and pattern, and with that we can build an algorithm to best anticipate potential anomalies, um, and address them proactively, and targeting to minimize the likelihood of an accident. So implementing real-time monitoring um, through digital twin and AI combined with predictive analytics plays a vital role in enhancing safety within the oil and gas industry. Leveraging this technique, we can significantly reduce the risk and create a safer working environment for everyone involved. We'll go into the role of AI, machine learning, and digital twin in modernizing well operation. So this advanced technology um, is revolutionizing our view on data. So AI and machine learning uh, uh, can can help us analyze big data, vast data sets, and from there we should be able to extract an insight from the pattern and trends that that we get from the data sets. From the from that data set, from the pattern and the trends, then we can create an algorithm to help us analyze through complex data sets and to identify pattern and trends. Um, some a lot of patterns, like in drilling operation, it's very small, it's very minor. It usually being ignored by us human. So when with the algorithm, we can actually extract this kind of misses that human can't identify. Um, from continuous learning, and then we can build the predictive capability. As more data become available, this algorithm can continuously improve their capability to predict. This means company can anticipate anomalies or failure earlier, and then from there we can optimize, we can tweak the operational workflow to to avoid those anomalies, and hopefully by that changes we can improve operational performance. So a little bit of benefit of integration. We have a lot of component in our operation. So five main, I would say, expectation from this is we need to have that system to enhance our decision making. It should also increase the efficiency, able to predict maintenance, to provide predictive maintenance, improve safety measure, and sustainability impact. Um, enhance decision. So by using data-driven insight, scenario simulation. Um, for example, in data-driven insights, BP use digital twin to enable uh, the operator to monitor all the reservoir condition continuously. In scenario simulation, on the other hand, Shell also utilize digital twin to evaluate different drilling strategies before they implemented it. So during the pre-planning, they run a few analysis, find the best case using a digital twin, and then they go into operation. So with this strategic planning and risk management, they we can see clearer understanding of the potential impact on the well performance. In terms of increased efficiency, uh, total energy in um, has automated data entry and monitoring processes, so freeing up human resources for more complex decision making. On another example is from Chevron. They uses AI to analyze data drilling. Um, also I mean, all the benefits is in improving the efficiency of the operation and reducing cost. On predictive maintenance, digital twin um, used by Siemens to monitor their gas turbine. So they can predict the potential failure. So gas turbine is very costly to shut down. Once you shut down turbine, you lose your production. So by predicting the potential failure, we can minimize the downtime and manage the maintenance costs better. Improve safety. There is real-time hazard detection, also training simulation. So like ExxonMobil, they use AI-driven analytic together with the digital twin framework to detect potential hazards in real time. Potential hazard can be red zone management. Somebody who was not wearing a hard hat can be tagged and alarm triggered. People sitting or walking under loads. A training simulator, there's a lot out there. Um, for instance, like ADI, you can send your driller, your drill supervisor to see and feel when they control the joystick, what will happen to the operation. Let's say during drilling too fast will generate cutting, a lot more cutting that you can clean out. It will create back off. It will create stuck pipe. So other than uh, visualizing that issue, we can find a way to reduce the risk. And then if stuck pipe occurs or back off occurs, what is the mitigation process that you have to take to minimize the impact of the stuck pipe, how to free the stuck pipe, how to control a well, all those things. Um, and then sustainability impact. So this is more towards reducing carbon footprint. Uh, like BP, they have reported that more efficient drilling process enabled by digital twin technology. So by this technology, they can track, they can record the carbon output, and then they can also optimize that. So reducing wastage of fuel, all those things, um, streamlining the logistic aspect of mobilizing tools or whatsoever. A lot of things that can be monitored, and once you have the data, then we can know what to do to optimize your operation. Real-time operation capability. This is kind of like in Malaysia, real-time operation, especially for Petronas, they actually started in 2005. So um, it's at that moment it's like a second pair of eye to help monitor and provide interventions on potential anomalies, potential failures over at the rig site. But with COVID, uh, we can see smaller operator also start subscribing or um, focusing on real-time operation setup as well. So that's some of the benefit of integration. We'll go into digital twin. Uh, is there any question from anybody? Am I going too fast or you okay saja? Ada, eh? Okay. All right. Digital twin. I'm not sure about the syllabus. I think you should be learning it in uni as well. So digital twin is a virtual representation of your, I don't know, any assets, your processes, your PNID, anything. It can be anything. Your downhole environment, your seismic, um, production lines. So, but what digital twin needs is data. So, by having sensors, cameras, from that, the technology in digital twin, you feed it with the actual data, then you can see the simulation, and then you can analyze. From that analysis, then you can do the performance optimization. So with that, you can facilitate uh, your planning and optimization better. So digital twin, it's not only on the real time environment. You can use digital twin before that as well. During your front end engineering, when you do your well planning stage. Okay. Some key features of digital twin technology. So we have real-time data integration, obviously census reading, continuous data flow into the system, and then this allow detailed understanding of the technology of the workflow that you are handling, and then from there simulation capabilities. So from that simulation, you can generate a predictive model. On that predictive model, then if there is a trend deviation between the actual and the model, then you can know that there is something happening. There is an anomaly. Why is this changing? And why it is deviating from the model? We should be expecting this. Then you start to investigate what is the cause of it. So from there, you can do life cycle management. So with digital twin, you get insights. From that insights, it give you a better understanding, and then from there you can plan and allocate resources appropriately based on the historical data and predictive analytics. That's on the key features of technology. So digital twin technology application, this is three example. So performance monitoring, our performance metric in real time, pressure, temperature, flow rate. This is like when drilling operation, you are flowing at 1000 GPM, you should be expecting this much of pump pressure reading. So that's the model. And then once you feed the actual data, does the actual data fit the model? If it's different, then we need to find what is the issue here. So and then we can go into digital operation. Drilling automation. Same principle. We can see it's on an advanced application where you have the model, all those things running at the background, and then you linked it with the drilling control system of the rig, and then the drilling control system automation platform have its own logic to mitigate certain issue. So when there is deviation in your digital twin, it sends back that signal, or you need to pick up your string because you are having back off. So the digital twin system will send signal to the hoisting. It will pull up or of water. That's on the drilling automation part. So this relatively improve, not relatively. If we are talking about operation in Norway, they actually can, because they use robotic arm to do making up pipe stands and breaking out. Over in our water in Malaysia, the in sleep time usually between 5 to 6 minutes. In Norway, they actually operating within 3 minutes window to do that operation alone, to make up a pipe, picking up its off slips. So and then operational optimization. Yeah, by combining this, then you can refine, you can improve your operation. You can always drill with your optimal parameters. If you have routine sequence, it will be, I would say, perfectly done by the automation. One sequence to the sequence, so you can repeat the sequence with the precise input that you give the machine. So that's on the on the digital twin. Role of AI and machine learning. So we have four components: data analysis, predictive analytics, enhanced decision making, and automation of routine tasks. So we have talked about vast data sets. We have talked about real-time analytics. Um, like BP, uh, they employ AI to analyze seismic data from geological survey. By processing seismic data is a large volume of data. So by processing this type of data, BP is able to identify potential drilling sites with higher accuracy. So just from the seismic itself, um, let's say you have traditionally you plan 3 exploration well, or maybe sometime 5 or more for one area, to find the best place to build your platform, and then start your engineering process to plan your trajectory, blah blah blah, and whatnot. So by this application of machine learning and AI technology on seismic data, they were able to reduce the exploration cost, and make a better decision where to set their platform. That's on data analysis example. So predictive analytics. Uh, in drilling technology, I think we still have, I mean, to my knowledge, we still have a lot of work to do, because it's drilling or upstream environment. It's very volatile, I would say. Too many anomalies, too many factors involving it. Different stratigraphic, different geology, subsurface thingy, fluid itself, drilling fluid, different rheology can change. Um, But equipment failure have an extensive reach in downstream in facilities assets management. So they they integrated the PNID of an assets. They can build a 3D image by scanning using drone cameras or whatsoever, and then build a digital assets. And then from there, they run a digital twin based on that PNID. They know if this flow is restricted, which valve is faulty or need maintenance, all those things. So it's we can see a better um, example in predictive analytics in downstream sector. In drilling, for instance, stuck pipe, there's a lot of people building stuck pipe module. Um, some using decision trees, some using single data source to predict. But again, it goes to the dynamic of the drilling environment. Sometimes you get the signature, sometimes you don't. But the obvious anomalies such as back off, um, wobble trajectory, it's easier to detect. But like differential sticking, sometimes it's a bit tricky. Optimization, drilling optimization, optimizing the parameter. Um, like Petronas, we have the ROP optimization. So it uses flow rate, weight orbit, and RPM as an input parameter, send it to a machine learning module, get calculated, and then feedback to the system, and then you see the variation. So um, the logic will tell you which parameter to increase to have an optimal ROP. So it have good and bad results. Sometimes it gives you a good ROP when you apply changes, most of the time. But then it still have room for improvement. And then we go to enhance decision making. So um, again, BP uses AI to monitor equipment health in real time. Same example as before. As for scenario simulation, like Norwegian, previous Stat Oil, now it's known as Equinor. They are big in doing scenario simulation based. So they have what they call now drilling well on simulator. So you have your plan well, then you start feeding what if scenarios. If you have stuck pipe, what will cause the stuck pipe, blah blah blah. So that is done in a room with a drilling chair, a cyber chair, and then you have the top side visualization, and then you have the downhole visualization. So it's a way to work on your planning, and then from that simulation, when you are simulating, you find the issue, or probably I have to shorten this section to give better hole cleaning on the section below or whatnot. So it's in no way they have been in digital journey longer than us in Malaysia. So the work the engineer have to handle now, it's more on what we mentioned before, on critical decision making stuff. So for instance, they have a software to build to propose a trajectory for a field, and then they will go to a simulator. We have this kind of well. Uh, okay, come driller, you try to drill this well and see what happened. Okay, I want you to use this parameter, this speed, this rotation, and then this flow rate. The mark weight is this kind of mark weight. So they can play around with a lot of stuff over there. So it's still a journey from our side. And then lastly, to automate the routine tasks. This is also drilling automation is going towards this direction. So now you like Slumberjee, sorry, no, not Slumberjee, SLB, Halliburton, Baker, they have this automatic directional drilling automation. So now you have automation on your directional drilling, you have automation on your surface equipment, and then you have automation on your downhole condition. So this loop cycle is um, automation routine for drilling. We have run three project with Petronas on this type of automation. So obviously it does provide a better efficiency because all the repetitive function have been replaced by automation. So in terms of handling anomalies, not all, but several of, I think there's 5. If we're talking about the system that we bring into Petronas, they have 5 um, anomalies that can be handled by our system. We'll talk about that a little bit later on the case study. Okay. Let's see one video on stuck pipe event. This is from Spark Cognition. They built an AI model to predict stuck pipe. So, okay. Let me start again.
Successful. In high-cost, high-risk drilling environments, drilling operators may encounter a critical challenge known as stuck pipe that threatens successful well completions. Stuck pipe can bring drilling operations to a complete halt until the drilling string is freed. It is one of the most expensive problems that can occur during a drilling operation and is a major contributor to non-productive time, which continues to comprise 20 to 25% of annual rig operating time. While physics-based modeling is unable to flag leading indicators with enough advanced warning, predictive analytics for anomaly management and machine learning-based modeling approach can detect and prevent drilling anomalies such as impending stuck pipe failures well in advance. Spark Cognition, a leading industrial AI company, offers a robust predictive solution that helps drilling operators identify and prevent stuck pipe events. In our recent case study, we deployed our machine learning models across multiple wells and drilling rigs for a large operator in the Middle East. And the Spark Predict product for anomaly management predicted 79% of overall drilling anomalies, including stuck pipe events, with up to 6 hours advance notice, saving the customer upwards of millions of dollars in drilling costs and downtime. In past offshore deployments, Spark Cognition increased the ability to identify unexpected events by 75% and more than doubled previous lead times. By detecting anomalies that indicate stuck pipe in advance, operators are able to not only better plan for or even avert stuck pipe events, but also mitigate drilling dysfunction and optimize drilling operations, enabling safer, more predictable operations. To learn more about how predictive analytics and machine learning-based modeling can help prevent stuck pipe events, contact us at info@sparkcognition.com.
I cannot cut the last part because I take their video. I have to include that. Okay. All right. Before we go into case study, do you have any questions, or I can continue? Okay. So this case study, the system that we use is Drilltronic. It's a rig automation system by Sekal, a leading Norwegian technology. Um, okay. Before we go into Drilltronics, into the technical part, so rig automation. From here, we should see insights and then have an efficient and safe operation. When you talk about automation, the simplest example is automotive. Automotive. So in general, there's actually 6 level, but level 0 is manual. So I exclude that. I just classify it as 5. In general, there is known 5 level. There is level 1 is human control with machine. Human suggest option. That's level 2. Level 3 is computer suggest options. Level 4 is computer propose action. And level 5 is full automation. When we refer to automotive industry, level 1 will be driver assistance. This is common. Um, it's like your lean assist. Level 2 is partial automation. Is kind of like a adaptive automation, like the one in controlling your distance between the car ahead of you. Conditional automation, level 3. This is an example is like Audi A8. It has a features traffic jam pilot technology that allows autonomous driving in specific conditions. So you can be hands-free in traffic jam, and that's kind of on level 3. Level 4 is Waymo taxi. We don't have it here. I think the US, they have a lot in US. So this vehicle, it can navigate into complex environment, but limited to location lah, and cannot operate in bad weather. Full automation. Also, Waymo is working on it. Waymo is working on a self-driving vehicle that aims to operate independently across various environment. So if we link this to drilling automation, automotive, if you look at the lane axis, your right and left lane, you can imagine that as your pour and frac gradient limitation on your left and right. And then your adaptive control, which is the distance to the car ahead, that can be your ROP optimization, where you can slow down the speed or accelerate when the condition is safe. So that's the linkage between, I mean, the easiest way to imagine drilling automation towards automotive. Okay, Drilltronic, it covers level 3 and level 4 drilling automation. So in level 3, this is when Drilltronic operates alone. Uh, it it will handle most of the drilling tasks under specific condition. So the driller still need to be in charge when there is unpredictable scenarios, such as when you are tripping out, suddenly you have stuck pipe. At the moment, there is no automation to mitigate stuck pipe or replace driller to perform the task to free the pipe. So when the pipe is stuck, driller have to take control. So that's level 3. Level 4 is high automation. This is when we combine all three automation that I mentioned before. You have the directional control automation, you have the subsurface automation, you have subsurface condition automation, and then you have the topside automation. So that's level 4. Before I go deeper into in Sekal technology, let's see this video.
As our world turns ever more digital, industries are challenged to become safer, more efficient, and predictable in their delivery. The aviation and automobile industry have been successful frontrunners in their drive towards autonomy and automation. Sekal is taking the same leading role in the drilling industry, challenging existing truths, forcing competitors to change tactics and pace. Today, drilling operations are surprisingly inefficient and unpredictable. Up to 50% of all operations run into major unforeseen problems, causing costly delays, unnecessary sidetracks, and lost production. Today's drilling practices are still best described as fumbling blindly in the darkness. Sekal is the globally leading software provider, bringing autonomy to the drilling operations. We use advanced dynamic modeling combined with artificial intelligence and machine learning when improving the planning and execution of drilling operations. The Drill Scene Artificial Intelligence software compares Sekal's advanced digital twin to the actual ongoing drilling operation. Deviations give early notifications, allowing the team to react in time. Like the GPS in a car, notifying the driver when the route should be adjusted. Drilltronics optimize the reaction of the drilling machinery in line with the dynamic and changing downhole conditions. It safeguards the well, improves efficiency and supports the driller, just like traction control. Adaptive cruise control and ABS brakes supports the driver in a car. Combining our products give the ultimate client value. Drilling becomes safer, more consistent, efficient and predictable. Secal is the industry leader. Allow our intelligent software solutions to drive your performance to the next level. Right now, we are powering autonomous drilling.
Okay, bombastic. When it's marketing material, everything bombastic. So, okay, Sekal is our technology partner to Fasmia. So it have three software. It have Drill Expect. This is like a simulation, pre-run simulation tools to generate your top and drag, to see your swap and search effects. Uh, you can we can build a transient cutting model transport. Transient cutting model transport. Yes, sorry, the other way. Transient cutting transport model. So we can simulate how with the parameter that you drill, how much cutting we generate, and are we able to transport the cutting out of the hole. So drill aspect can also be used as a real-time tool when used combined with a drill scene. So all these three systems using the same physics model at the back end. So drill scene, we are using this using a WITSML data format. Can also be with zero. But drill scene is normal WITSML data transfer is 1 millisecond. 1 millisecond, 10. Sorry, every 10-second data. So with Drilltronics, it needs a dedicated server on the rig itself because Drilltronic is linked to the drilling control system where we take millisecond data into the system. So when there is a micro fluctuation or micro spikes in your data, the system can see that and react on that. So this is the three platform, the three software from Seca. So this is rig automation general workflow. So we have the control system. We have the technology enabler. So Sekal is one of these. SITS one of these. Is one of the technology enabler. So then you have automation platform. Automation platform usually links with the drilling control system provider. And then you have the automation technology. So automation platform and drilling control system communicate both ways. So it reads high frequency data, it will transfer to the automation platform. Automation platform will monitor for deviation So this is where the digital twin sits in the automation technology. So if there is any deviation, the technology will send command to automation platform. Automation platform will send command to the machine, either to hoist up on the drawworks, either to slow down rotation or shut down rotation, slow down the pumps. This is only a simple way to understand this. So basically, you have one, two, three levels to enable automation, rig automation. Okay, on Drilltronics. So this is the rig automation for Drilltronics. So it automates. There is three functions. So we have dynamic safeguard, and then we have automated safety triggers. These two functions. So dynamic safeguard will um, will protect your swap and search function. So if you have let's say you are pulling out of hole, your pore pressure and your mud weight is very close. So you cannot be pulling out too fast. When you pull the string, Viltronic will control the pulling out speed of the drawer. Max flow is it will auto adjust your flow rate based on your point frag as well. Safety triggers will cover hook load, will cover top protection and back off protection. And then with the electronic also you can have automated function. So this automated function covers tripping speed, pump start up, pump shut down, friction test. Friction test is the torque and drag test, and reciprocation function. So by repeating this function, you will have identical period of time to start your pump. And then for friction test, you have to be performing your friction test with the same parameter to get a good understanding of your torque and drag chart. We'll look into that later. I have one example on that. So all these three functions will go to the autonomous optimization and application of physical drilling action. Then it links towards the drilling control system. So the previous slide is side to side. This one is specific to Drilltronic function from right to left. Okay, this is an example of a rig control automation, drilling control system automation platform. So on their, they call it human machine interface. You can see this screen on the left. When you open menu, you will see a lot of listing on functions. What do you need to? What do you want to do? You want to circulate? You want to reaming? You want to come out of hole? So for this example, it's the driller choose a drilling option. So once the drilling option, I call this the recipe: adding stand, taking weight, ramping up flow. So there is a simple function with less detail, and then there is a more elaborate automation flow when you want to start drill. So this is once the driller start the automation, the system will pick up the stand, will pick up the string, and then it will automatically lower the string while ramping up, wait for pressure to stabilize, and then it will automatically start the rotation, and then the tag bottom. Once tag bottom, it will go to drilling automatically. Towards the end of stand, it will drill off a little bit, and then it will pull back, go to box height, meaning box height is where you put the slips. Once you are at box height, the pump will drop, rotation will stop, and then it will disconnect the top drive from the drill pipe, and then go and repeat the next stand by adding the stands for drilling the next stands. Okay, this is the full features of the human interface, Novos human interface. This is all an individual apps. You have rotation apps, you have circulation apps, equipment control apps, tech bottom, and then they have many more. Every time it's just like your phone. When you open an app, it will show an icon up here. So this is the Drilltronic apps that is built into Novos HMI. Okay. This is how the driller start. So they release the pipe connection and then set the slip off, and then the automation platform starts. It starts with pump start up, not very clear, but the pink color is the model, and then the blue color is the actual data. Okay. Example, pack of protection. The pack of protection means protection means that you want to avoid the hole from packing off, usually from drill cutting or solid accumulation. So by doing so, we should expect a better wellbore integrity, because you are not fracturing the formation in the event of back off. This is a simple way, not a simple way, but you have pressure, you have flow rate. This is kind of the logics that Drilltronic have built in to uh, to trigger the anomaly monitoring. So see if I can use this. Where is hmm? Why can oh sorry. Okay, the first color, yeah, this one. So this one It's susah nak guna ni. Kita guna pointer. There's a pointer. So the black one, it goes to the maximum pressure limit. Once you see that it reach pressure limit, it will drop down the flow rate. Just follow the black line. You see the black line is just a smooth line, and then it doesn't shut down the pumps. It continue with the black line, it drops back, and then continue. But if the pressure exceeded the limit, the maximum limit, because this one go exceeding, it straight away shut down the pumps automatically. And then the blue line, it drops the flow, but the pressure still initially decrease when they drop the flow, and then it increase back. And then the system will send a command, shut down the flow, shut down the mud pumps. The yellow line, the yellow pressure, it's cyclic. It's not stable. This also will trigger a pump shutdown. Boom. How do I go to next? Okay, this is an example. I was not able to generate generate macam mana nak go back ke ni arrow. dia lekat dekat pointer. Tak apalah, pergi dulu. Okay, just a little some background. The operation was drilling 12 and a quarter hole section. They were drilling until 2,152 meters. The directional driller did a downlink using RPM. When they downlink to 117 RPM, the pressure spikes. Once this pressure spikes, exceeded the maximum maximum margin, the flow rate, the system send a command, it drops the flow rate by 20%, and then it hoists the block upward automatically. You can see here the pressure kind of not stable, and it still sits on above the model. The model is the black dotted line, black dash line, sorry. Because of this, the system send another command, you need to shut down the pump. Boom, it shut down the pump. This sequence is within 20 seconds. The back of protection sequence. So once drillers see this, it took him about another 20 seconds to evaluate his panel. What is happening here? Is everything good? And then drillers start staging up the pumps. Because we have back off, he staged up the pumps. Slowly. You can see here, they were pumping at 816 when it reduced the flow rate over this end. You can see where the actual pressure is. Before, when the pack-off happened, it sits at 2,500 more or less. After that, when the driller staged up the pump, the pressure was around 2000 psi with 816 GPM. And then slowly they increased back the flow rate, and then they did a whole kiln circulation before they continued drilling. Okay, this is one example. Pump startup. Pump startup. This is the theoretical line. This is based on our input. So if we will have time to flow for the first stage, 300 liter per minute over here, and then 150, and then it will ramp up to drilling rate at 1,100 liter per minute. If we do manually and then we plot back this sequence of just pumping, starting the pumps, you will see this kind of plots. Usually at, at the start is relatively close, but towards the top where you ramp up to drilling rate, it varies so much. And with automation, although the dataset is not large, but we can see the consistency when we use machine to handle this function. So this is within 75 second. 75 second, you have a stable pressure to continue drilling. Over here, it can go much longer. Either they do it too fast or too slow, but this depends on the pour and frac of your formation. Next, friction test. So friction test is to provide consistency on the input parameter to get your results. So when the stand down or after you circulate, when it goes towards the friction test function, it will pick up your stand a little bit, about 0.5, 1 meter, and then it will stay stationary with a constant flow rate and RPM as per what you set in the application. After the at the end of this point, the rotation will stop automatically. It will hoist upward to take your pickup weight, with or without flow. That depends on your setting, with or without flow, and then it wait a little bit before the turnover, and then it will hoist down your block to take the slack of weight. So this is how it looks in a manual friction test. So the rotating of bottom period is not consistent. The lift distance is not consistent. The slope sometimes same, sometimes not. And then the downward distance also, I mean, the slopes sometimes different from one to another. And then when you introduce automation, you will get this type of features. The starting point sometimes does not uh, does not start the same, but the period of rotation of bottom period here, the slope, the distance, the top, it can be identical. And then from this, it gives you more confident to read your top and right output. This is a top and right output from drill scene. So drill scene pick up our system pick up the top and rack data automatically. So with the consistency, you can see if there is a deviation, like an slight increasing in pickup weight, and then increasing in slack off weight, would suggest an increase in ROP, which of course increase cutting loading. And you can see here the red trace, the ROP slightly pick up, which correspond to the increase in pickup and slack of trend. Another one is over here. They drop the RPM here to drill coal interval. The ROP also drop. And then once they finish with the coal interval, they increase the ROP, everything increase. So this is another signature of increasing cutting loads, but it's related to ROP. So probably it's not uh, impacting the wellbore integrity itself. Probably it's not enough to create a backup whatsoever. But it just show that when you have consistency in your input parameter to do your test, the output can be easily interpreted. Okay, swap and search. So and search is a semi-automatic function. So in theory, if your core and frag is have a wide margin, in most cases, let's say your mechanical limit of pulling out your 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 derrick, your sheave can handle a maximum limit of 1 meter per second, for example. If your operating window is wide, you can actually pull every time to the limit, to your mechanical limit. So that will save you time. But if your subsurface margin is narrow, then you don't want to pull too fast. You want to be within your margin. So if it's manual, the driller have to see the indicator and then control the speed. But in automation, driller can pull the joystick to the maximum, but the actual speed of the tripping is controlled by the system, by the machine. Just for example, on this one, um, we cannot do anything this part because it's a narrow margin, too narrow, very close. The mud weight and the pump pressure is very close. They have to pump out of hole. although we can pump out to 1.1 meter per second, but operationally, we don't want to go too fast because we don't want to potentially swap the well. In terms of analysis, it doesn't suggest that we will swap the well, even if we pull at a faster speed, but operation-wise, they dictate that, no, we want to pull this much speed only. And then from 2,200 meter, they were able to pull on elevator. Um, you can't see the difference because the gray line is the actual speed. The blue line is the electronic speed. So you can see the actual speed is following the theoretical speed. So the system is being utilized to the max over here. And then as we go shallower, you have to do flow checks, you have to handle the aviation, all those things, so they slow down the speeds. This is a video and how it actually, it's a playback, but you can see how to play this. Okay. Macam mana aku nak keluar daripada pointer mode ni? Okay. Let me pause. I'll try to, okay. This one, too much. This one is the static equivalent static density. This one is swap pressure. So you can see with the pulling, this is the pore pressure over here. Susahnya nak lukis ni. So this is pore pressure. So you can see the swap pressure is not crossing the pore pressure with the automation. So this is the block velocity going, this is pulling out. So this is your maximum limit. This is your swap limit. So you can see the actual speed is not crossing over the yellow shaded line. So it's being maintained within the speed limit suggested by the system. Wait. Right. Okay, it's just, there you go, you pull. And racking back the stand, going down to pick up the stand, and then pull. You can see the swap pressure never exceed the pore pressure. That is one of the benefits of using swap and switch protection. Okay. Okay, that is all on the example, real case example for drilling automation technology. So it's using a digital twin. Can't really show the AI and machine learning function as a whole from the drilling automation. Um, anyway, and now we are almost at the end of our session. So as technology continue to evolve, the potential for fully autonomous drilling system for sure will expand. It will reshape the operation across various sectors. Digital twin and AI are not just trends; they are transformative technology. Hopefully, with the correct implementation strategies, a clear direction from the organization, it can give you results, improve in efficiency, higher standard of safety, and sustainability of the oil and gas industry. Um, so yeah, enhance efficiency, safety improvement, and reducing costs. These three component is everywhere in. You can see this everywhere in our client Petronas, Shell, everywhere. And this is the key target of any initiative that they started off. So when you start a job, start a project, find a pinpoint, link it with efficiency, how the current practices uh, factor in safety and what are the costs. And then by implementing the system, what is expected increase in efficiency? Can it increase human safety or safety as a general? I doubt costs will reduce. I mean, operational costs probably, but then they will always ask about what is the cost for the implementation. And that usually will be high. So yeah, you have to be smart on your calculation. um, this is just an article from GPT. Um, End-to-end solution and beyond. I am not a fan of single solution can solve everything. I doubt it can be done because, for example, like Sekal technology, no company in the world at this moment reach the level what Sekal have done with drilling automation. So this is a rendering actually, like a flow chart. If I'm not mistaken, this is based on Halliburton. So you have multiple domain involved. You have engineering and well design, project management, finance, procurement, all until rig automation, advisory, real-time operation. All this function relates to your well construction. So it's one, it's preference for our client. Somebody prefer different solution for real-time operation, for example. And then well engineering, they want to use a different provider. You can have all this, but then the key differentiator in this workflow For me, ideally, I would want to have one independent platform where whatever function that I need can connect to this platform, and then either I can build on my own solution, my own display, my own dashboard, or I want to integrate a dashboard, a solution from a tracking mechanism from other vendor. So I would like to have the capability to pick and choose what I want, but this vendor neutral platform have to have the capability to integrate all this, and then it need to flow. The data need to flow in and out of the system. So with that, ideally, with time, you will build a robust environment for your organization. And then if you want to change provider for instance, inventory management, because you have all this, you have this platform, you have your company standard, blah, 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 whatnot over that platform. So when a new inventory management provider came in, they plug in the system, they can pull your standard, and then they can pull your data, so it's ready to use. So that's the ideal situation going forward, lah. But going there, it will be a battle because everybody say their product is good. That's where the organization have to have plan to find the best solution, because the investment is very, very big. You don't want to start something and then halfway or even you finish and then the system doesn't work. It will be very, very bad. So Shell, in their digital twin initiative, they were able to build or facilitate a platform, an environment that 140,000 users across 70 countries to access it real time and collaborate for world's operation. 1,000, 140,000 people across 70 countries. But Shell, frankly speaking, is an organization that really do their background work. If they have one software, let's say currently they are using well plan for for their well construction design, either for anti-collision, well planning, I mean well engineering, hydraulic, torque and drag, load analysis, casing stress check, blah blah blah. For as an example, if they want to implement or move from this platform to a new platform, they will they will spend their time to test this system. If it takes a year, they will go through it. They will test, they will check on the formula used, the physics model used in that solution. They will spend they will rigorously test the system before they implement it. Because what Shell do, once it's tested, proven, usable, efficient in one domain, usually in Holland. Once they test that, everything signed off, and then they will start deploying this to all their assets around the world, one by one by one. That's how Shell operates. So yeah, In terms of SECAL, this is what will be coming, I think, early next year. They have auto smart ROP, smart auto ROP. It's like an adaptive driving. So they build out an auto ROP optimization machine learning model, and then they top they top up, they combine the readily continuous well-bore system in Drilltronic physics model, and then they build another ROP constraint server. They link all this to provide an auto ROP solution. So if you see this triangle, the second model, uh, in principle, they have hydraulic model, they have mechanical model, they have thermodynamic model. But with auto ROP, they add another model here, which is bit response. So, like adaptive constraint, you drill, for example, you drill 100 meter per hour, and then your hole is loaded with cuttings. Without digital twin, you will not know how much or where the cutting that you drill distributed along the well. So running smart auto ROP within the electronic environment, if at certain bed height or distribution of the cutting is too much, and the hole is, it cannot handle, the auto ROP system will take control. If it's in active mode, it will take control. It will reduce the speed, let the cutting clean out a little bit before continuing. So it adapts with the downhole condition. So that's on what's next with SECAL. Okay, I have gone through this, the 7 factors. Well, ideally, in our real world, this kind of road we should expect. It's winding up and down. Sometimes you're gone, you're lost, and then come back. But is this kind of lane a journey can be reached? Is it possible? I think it's possible. It's still winding up and down, but at least you see a clear path from start to end. So um, I think there is 5 factor that need to be, I mean, as a closing, need to be considered uh, to have a successful digital twin adoption. One is the data security risk, and this is a big issue. If I'm not mistaken, last 2 months, this is October. If I'm not mistaken, in July, Halliburton had a breach in security. So it's a big deal over there. A lot of downtime, but globally also many major oil company have incident related to data security. So um, you need to find a good provider or to handle your infrastructure, your data. So implementing robust cyber security measures, encrypt the data, multi-factor authentication, um, as simple as a single sign-on. There's a lot of companies still don't have single sign-on. That's one of the key features of data security, which is your email credential. Then skill groups, skill gaps of workforce. This is a big issue as well. Um, the industry developed too fast. Your well experienced people uh, pools is shrinking. The new engineer is expanding a lot, and then the middle entity. I mean, let's say is the knowledge transfer between top to bottom is tricky right now. So that's another challenge. So by that, to 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 reduce this gap, obviously the organization will need to train people, develop them, of course, investing, collaborating with education like university. So like doing internship, upskilling, either you personally invest yourself to upskills or the organization send you somewhere to upskills. Integration complexity. Which is if you have existing system, it can be complex and resource intensive. But then there probably be a new technology built in a new uh, platform that is equivalent to your legacy system. That can be easy to implement. But if there are none, then you have to have a planning how to work, and then I don't know, maybe investing into those company and build a joint venture to build the system that you want. If it's a new system, then you have to start pilot projects. You have to start proof of concepts projects. Utilize standardized protocol for smoother integration, and regulatory compliances. Uh, this is, I think it's a gray area for me because it changes too much. But if if we have a proper regulation, it have to be stringent towards data management and operational safety. Um, Implementing new technology have to ensure this uh, as their priority. Uh, then proactive measures. Company must stay informed about regulatory changes and incorporate compliances consideration. Engaging with regulator during development can align technology implementation with a regulatory requirement. So Yeah, this is the um, five component I say that you need to put on top of that seven success criteria in your digital journey. Cybersecurity is very important. Regulation, get a good understanding on that. Work with it. Don't divert from it. Um, yeah, and then that's it from that's all from my presentation. We will go to Q&A. We will have
All right.
and
Thank you, Tunku.
yes.
So now we open to any questions from attendees. Please feel free to ask or drop your queries in the chat box. Any questions from our attendees? We assume there are some questions from the attendees. And before we wrap up our second session, we kindly ask you to scan the QR code provided to share your feedback, which will help us to improve experience in the future sessions. So, as a reminder also, our third session is scheduled for 11 November 2024 and will be delivered by Atif, our head of training and drilling. So, for full details on the event, you can kindly refer to our event template. And also, if you have any question regarding today's topic, you can just feel free to reach out via our email shown in the QR. And lastly, on behalf of Fazbear Technology, we truly appreciate your support and thank you for joining us for today's sessions. And we look forward to seeing you in our next sessions and wishing you a wonderful day ahead. Thank you for attending our sessions.
Thank you very much. Bye bye. Assalamualaikum.